So dear students, you are welcome in this lecture. Now we will discuss problems of supply and availability of nutrients. So there may be certain factors which limit the supply of nutrients to the plant root. So we will discuss, and we will also see what are the factors that affect the availability of nutrients in soil to the plants. So learning objectives are to understand the cycling of nutrients in the soil. Cycling of nutrients in the soil means how they are coming into the soil and how they are going out of soil. That is cycling. Discuss the factors influencing supply of mineral nutrients into the soil solution. Because you know nutrients are taken up by plant mostly from the soil solution. So there has to be supply of the nutrients into the soil solution so that plants are not getting any short supply of the nutrients. Now some terminology, you are already knowing it. Adsorption. Adsorption is the taking up or uptake of molecules or ions. Many times students know that adsorption is just attachment of ions with the clay complex or organic colloids. It is not like this. Adsorption have some wider meaning. The taking up, uptake of molecules. So it also includes molecules and ions or ions at a surface, including exchangeable cations and anions on soil colloids. Base saturation, fraction of the total exchangeable cations that are bases or base cations, calcium, magnesium, potassium, and sodium. Buffering capacity of the soil. So most of the time, students consider it as related to soil pH. So most of the people take it in that sense, but some people have used this buffering capacity in other sense also. Like you get soil solution. Soil solution contain nutrients, and these nutrients can be taken up by plants, and these nutrients can be leached. Leaching can also occur from these nutrients. Then when there is deficiency of nutrients in the soil solution, some nutrients will come from outside. They may come from organic matter, they may come from exchangeable site or minerals. And then they will buffer the solution. So that is also buffering capacity of the soil with respect to nutrients. Similarly, there may be some other instances, but most of the time people restrict it to soil pH. Buffering capacity of soil, ability of a soil to resist change in concentration or activity of its constituent and its properties in response to external intervention. That is the broader meaning of buffering capacity of the soil. But sometimes, or rather most times, people write its definition as ability of a soil to resist change in soil pH. Ability of a soil to resist change in soil pH. So that is the definition of buffering capacity of the soil. This is in broader sense. Diffusion of nutrients. Ions in the soil medium move from a point of higher concentration to a point of lower concentration. That is your diffusion of nutrients. Ion. Ion can be atoms, groups of atoms, or compounds which are electrically charged. So it can be like ammonium. Ammonium is group of atoms. One is nitrogen, other is hydrogen. HPO4, it has hydrogen, phosphorus, oxygen. So atoms, groups of atoms or compounds which are electrically charged. Loss or gain of electron may be cation, may be anion. Nutrient mobility, ease with which nutrients move from one place to another in the soil. So that is nutrient mobility. So mobility can be within the plant system as well as in the soil system. Plant system, you know, N, P, K, Z, and Mg. These are mobile nutrients and their deficiency occur in lower leaves. N, P, K, Z, and Mg. And rest deficiency symptoms come in younger leaves and they are less mobile in the plant system. Similarly, certain nutrients are mobile in the soil system and some are less mobile in the soil system. Phosphorus is the example. Phosphorus does not move even more than 1 inch in the soil. So there are both kind of nutrients, mobile nutrients in soil and immobile nutrients in soil. We will see that. available nutrient, portion of any element or compound in soil that can be readily absorbed and assimilated by growing plants, means that can be used by the plant or it is in the usable form by the plant. Crumb is a soil, is kind of soil structure, a soft, porous, more or less a rounded natural unit of structure from 1 to 5 millimeter in diameter. Exchangeable ions, positively or negatively charged atoms, they are groups held on surface of a solid particle by attraction to charges of the opposite sign and may be replaced by other light charge ions in the soil solution. So exchangeable ions are actually part of the cation exchange capacity and anion exchange capacity. Cation exchange capacity means capacity of the soil to hold ions. What quantity of ions it can hold. That is your cation exchange capacity, and anion with respect to anions. Heavy metals, it has got several definitions, but most acceptable definition of heavy metal is that they have densities of 5 megagram per meter cube. I think it should be per meter cube, or greater. Means that is basically dependent upon density. Megagram means 1000 kilogram or 1 ton per cubic meter or greater. Examples are cadmium, cobalt, chromium, copper, iron, mercury, manganese, molybdenum, lead, and zinc. These are the examples of heavy metals. Isomorphous substitution. Isomorphous substitution is the replacement of one atom by another of similar size in crystal lattice without disrupting or changing the crystal structure or the mineral. So there are some silicate minerals in the soil, and those minerals have interspaces in them. In those interspaces, sometimes certain ions enter there and they get fixed, like ammonium fixation is there. Ammonium fixation is there, but what happens, a lot of ammonium can be accumulated into those layers, and that is ammonium fixation. If you apply potassic fertilizer or potassium, then this potassium will replace, it will release ammonical nitrogen that was fixed in the lattices. So whenever such cases are there, in those cases, one can apply potassium to increase nitrogen availability in the soil. Potassium can easily replace this ammonical ion because the ionic radii of potassium and ammonium is almost similar. So that is known as isomorphous substitution, the replacement of one atom by another of similar size in a crystal lattice without disrupting or changing the crystal structure. Crystal structure will not change, just substitution will be there. Trace elements present in Earth's crust in concentration less than 1000 milligram per kg. And if referring to plant nutrients, the term micronutrients is preferred. Now, trace nutrient is not used now, micronutrients should be used. Now, let us see what are different sources that supply mineral nutrients to the soil solution, because plants can take nutrients only or mainly from the soil solution. Of course, sometimes plants can take up nutrients directly from the exchangeable site also if their roots are reaching there. But most of the time they take nutrients from the soil solution. So it has a small fraction of total nutrient. The soil solution is not that much rich in nutrients. It contains very small fraction of nutrients. Nutrients removed by plants, first of all, by uptake, and then soil solution pool is depleted. There is deficiency of nutrients in the soil solution once uptake is there or active uptake is there. And then what happens, nutrients are readily replenished. A balance is maintained, equilibrium is maintained into soil solution by cation exchange. So from cation exchange, nutrients will enter the soil solution. So 4 important sources of nutrients into the soil solution. These are 4 sources where from nutrients will come into the soil solution. One is soil minerals. Certain soil minerals can decompose and they can release nutrients that can reach the soil solution. Exchangeable cations are in equilibrium with the soil solution. And if there is shortage of ion, a particular ion in the solution, it will be compensated, or ion from exchangeable site will enter the soil solution. Chemical compounds, like you add some fertilizer, some sources, they can also add these nutrients to the soil solution. Organic matter is, of course, a source of nutrients to the soil solution. So these are the four important sources through which the nutrients come to the soil solution. Now you can see this picture, sources of nutrient supply mechanism in soil solution for plant uptake. So you can see this is soil solution, and plant uptake of the nutrient is there. Then nutrient can come from mineral solubility. Some minerals can be solubilized, or weathering of the mineral can occur, and some will be provided to the soil solution. Mineral solubility, like phosphate is fixed with calcium phosphate or aluminum phosphate, and then it can be solubilized by some amendments or some other practices. We can make this mineral solubilized. They can also reach soil solution, or weathering of rocks can also result in mineral supply to the soil solution. Surface exchange, that is for cation and anions, means from exchangeable sites, the nutrients can come here, and there may be losses of the nutrients from this soil solution. Losses by leaching, drainage, or surface runoff. So part of the nutrient can be lost from the soil solution. And this organic matter can also supply nutrients to the soil solution after mineralization and decomposition. However, soil organisms help in the decomposition of organic matter. They can release nutrient into the soil, but at the same time, soil organism can also take up nutrients from the soil solution. So these are few mechanisms of related to soil solution, gains and losses from soil solution. Now, readily, moderately, or slowly available nutrients. Many times for different nutrients, we call them readily available, moderately available, slowly available, or labile pool or non-labile pool. Some terminology is used. So absorption of nutrients depend on their forms. Phosphorus is speedily available as phosphate, H2PO4, is the most preferred form by the plants. And then next in the order is HPO4, but unavailable rapidly in tricalcium phosphate or apatite forms. So if it gets 3 minus charge, then it is less available to the plant. So you can see this is readily available H2PO4, this is moderately available, and the phosphate form is your slowly available form. Nutrients in soil solution have to be rapidly available. They are rapidly available. But nutrients on exchange complex are also available for absorption, but not quite as readily available as from the soil solution. So they actually have to enter the soil solution, then they can be taken up by the plants. Now you see relative availability of different forms of inorganic P to plants. So first column, inorganic phosphorus in soil, then source, and then what is the status of availability. See, mineral phosphorus and very strongly adsorbed phosphorus. This mineral P and very strongly adsorbed P. So this is in the form of calcium, iron, or aluminum phosphate minerals, and very strongly adsorbed phosphate. So this is very slow. Availability to plant is very, very slow. Then number 2 category is strongly adsorbed P. Strongly adsorbed P. P adsorbed to clay and other mineral surfaces. So availability is low. Weakly adsorbed P. P adsorbed to clay and other mineral surfaces, and availability is high. And then solution P, H2PO4, HPO4, it can be very high. I can put it very high availability to the plants from the solution P. Now, cycling of nutrients in the soil. Cycling, as I told you before, input and output, addition and removal. So input into the soil and output from the soil is cycling of nutrients. You are cycling them. So following points are important in cycling of nutrients in the soil. Plant uptake reduces the amount of nutrients in soil solution. As plant roots remove nutrient from the soil solution, there may be deficiency of nutrients in the soil solution. Nutrients adsorbed on minerals or humus get dissolved and enter the soil solution. So supply will be restored, or it will be equilibrium from the exchangeable sites or from the colloids. The mineral will come to the soil solution. Nutrients added as minerals or organic manures increase the ion concentration in soil solution. If you are applying fertilizer, phosphatic fertilizer, nitrogenous fertilizer, or potassic fertilizer, they will make your soil solution rich because their nutrients are mostly in directly available forms. So, or within a week, they are converted into available forms like urea. It supplies nitrogen, and within 8 to 10 days, it will decompose, hydrolyze, and produce ammonium and nitrate. So they can immediately become part of soil solution. So nutrients can be added as fertilizer, minerals, or some organic manures. They can also increase the concentration of soil solution. Of course, organic manures will take time, but even in certain organic manures, inorganic minerals may be there, like in farmyard manure. Farmyard manure may also contain certain nitrogen in inorganic form because it is already decomposed for 6 months. Minerals in soil dissolve to buffer. Minerals in soil dissolve to buffer or resupply. Buffer means resupply here, the soil solution. So buffering of the soil solution is important here, and that can be buffered by fertilizers, organic sources, or exchangeable sites. The soil organic matter undergo decomposition and supply the nutrients. Soil microbes absorb nutrients from soil solution. They can also absorb nutrients from soil solution and release nutrients back to the soil solution after death. Of course, they will take up nutrients from soil solution, but they cannot keep it forever. Ultimately, they have to return it back to the soil solution, and they will do so only when they die. Till they are alive, they will not like to give anything. But once upon their death, they will release back minerals into the soil solution. The biological nitrogen fixation increases nutrient availability, because if you know that legumes, when they fix nitrogen, there is concurrent transfer of nitrogen into the soil. So some of the nitrogen fixed in root nodules also leaches down, and that can be part of the soil solution. So it may increase nitrogen concentration in soil solution. Biological nitrogen fixation by legumes or by other bacteria, by some bacteria. Nutrients are removed by crop harvest, and here I wish to tell you that there are number of free living bacteria that also increase the nutrient availability. It is not just nitrogen fixing bacteria like your Azotobacter, Azospilum. A number of free living nitrogen fixing bacteria are there in the soil, but some of them also mobilize phosphorus. For example, your Azospilum brasiliensis. Azospilum brasiliensis is also good for mobilization of phosphorus in soil. It has been proved that this bacteria, Azospilum brasiliensis, it also mobilizes and makes phosphorus available in the soil. And it also acts as a growth promoter of the crops. Similarly, there are some other fungi which also prevent the insect diseases in plant. So certain microbes are useful in the prevention of diseases also, not just nutrient mobilization. So large fraction of certain nutrients lost by erosion, leaching, runoff, volatilization, etc. So of course, losses also occur for the nutrients. Of course, they enter the soil, but they also go out from the soil. Now, this is important part. In the remaining part of this lecture, we will discuss these 7 points. Factors influencing the supply of mineral nutrients. So there are n number of factors. Means there are so many factors that will govern the supply of mineral nutrients. It is not easy to cover all the factors. It means you go on writing, counting, many factors will affect the nutrient supply to the soil solution or availability of the nutrient. It is not possible to discuss all the factors. Here we will discuss the mobility of nutrients in solution, soil, which affect the availability or supply of the nutrients to the plant. Availability and supply. If it is supplied, and then it is available. If it is not supplied, it is not available. And what is supplied? Nutrient in available form. Nutrient in available form is to be supplied to the plants. So important factors are mobility of nutrient in soil. Nutrients which are mobile, their access to the plant root is quite easy. And nutrients which are not mobile in the soil, their access to the plant root is limited. Similarly, cation exchange capacity and anion exchange capacity. If these capacities are lower, then the supply or they will hold less cation and less anion. That means the supply of the nutrients will be less. If you have higher value of CEC, AEC, you will have more supply of nutrients to the soil solution. Base saturation in the soil. Higher the base saturation, more is the availability of the nutrient. Buffering capacity with respect to nutrients. So higher the buffering capacity, more is the availability. Soil pH, you also know the role of soil pH in nutrient availability. Certain nutrients are more available in acidic pH and few nutrients are available more in basic pH, and most are available best in the neutral pH from 6.5 to 7.5. You got maximum availability of almost all the nutrients. So pH is an important factor. Soil organic matter and its decomposition by microbes is very important. You know that soil organic matter has more than 1,000 roles. It improves physical, chemical, biological properties of the soil. If soil properties are improved, they will definitely lead to retention of more ions, more nutrients in the soil, more supply to the plant, and better plant growth. Physical condition of the soil will affect the nutrient supply. If your soil structure is disturbed, it is broken, no proper soil structure, compaction is there, hard pan is there, so it will not help in getting better supply of nutrients in the soil. So all these factors are going to affect the nutrient supply. But you can see water is very important. If there is no water, where from you will get soil solution? Soil solution means nutrients in water. When the nutrients in water in available form are there, so that solution is your soil solution. So if there is no water, how you will get the soil solution? So water is very important, and in the mass flow of nutrients from one place to another place, you need water. So water is also important in the supply. Similarly, temperature. I'm not discussing here temperature, but temperature is going to have a role in the uptake of the nutrients, availability, decomposition. Number of things will be governed by temperature in the soil. So we are not going to discuss those factors, but important one we will discuss here. Now, mobility of nutrients in soil. This is number one factor which will affect the supply of mineral nutrients to the soil solution. Mobile nutrients in soil, mobility varies with ions. For example, nitrate and sulfate and chloride and even boric acid. They are more mobile, not strongly attracted to exchange sites. They are not strongly attracted to the exchange sites, soluble in soils, readily move through the root zone with water. So they are easily moving in the soil. Therefore, leaching losses are quite more in case of nitrate, sulfate, chloride, because they are negatively charged and there are less quantities attached to the exchangeable sites. So remaining part remains in the soil solution. So they are mobile in soil and readily move through the root zone with water. Mobile nutrients within the whole soil volume occupied by plant root system are available for transport to the root in percolating and transpirational water. Relative mobility of each nutrients depend on soil pH, temperature, moisture, soil texture, clay type, and organic matter content. So all these factors will affect the relative mobility of the nutrients. Now, immobile nutrients in soil. So immobile nutrients in soil, these nutrients interact with mineral and organic surfaces, are less soluble, do not readily move throughout the root zone. Relatively immobile in soil, plant roots access these nutrients from a small volume of soil surrounding individual roots. So that is the limitation. They are not mobile, they are less mobile. So they are distributed in less volume of the soil. So their accessibility by roots is less. Plants create a small zone around the root that has very low concentration of these immobile nutrients due to plant uptake. So we need to understand that what are the immobile nutrients in soil and what are mobile nutrients. So this knowledge will definitely help us in the management of nutrients. If we know the mobility, we know that nitrogen is mobile in the soil. Therefore, it can be applied on the surface. Top dressing can be done, and it is usually done by farmers to improve even efficiency of the fertilizer. But see about phosphatic fertilizer, they are normally not broadcast applied. They are not top dressed also in the standing crop. They are always suggested as basal application, phosphatic fertilizer. And that is near to the seed also, so that roots can easily access this phosphorus because it is less mobile. So this knowledge is very, very important in management of the nutrients. Therefore, we are studying it. The concentration gradient allows diffusion to transport nutrients that are further away from the root surface toward the root. So this is, they will move from higher concentration to lower concentration by diffusion, but their movement will be very slower movement. If the soil has a high buffering capacity for an immobile nutrient, then the solution can be replenished and diffusion continues. So, but soil should have high buffering capacity, means it should be replenished into the soil solution. With a low buffering capacity, solution concentration and diffusion ultimately decreases, causing a nutrient deficiency. So this is a property of the soil. Buffering capacity means to resupply. Buffering means resupply the nutrients into the soil solution. Now, the important points for nutrient mobility in soil are, if we summarize these points, then the mobile anions, sulfate, nitrate, chloride, quickly move through the root zone with water. The mobile nutrients are available within the whole soil volume uniformly. This is also an important point. The immobile nutrients interact with exchange surfaces and are less soluble and move slowly through the root zone to the root surfaces. So therefore, availability of these immobile nutrients is less to the plants. Ammonium, potassium, calcium, magnesium are more soluble and mobile than micronutrient cation, phosphate, H2PO4 and MoO4, molybdenate. These important points continue about mobility of nutrients. The knowledge of nutrient mobility is useful in deciding the nutrient management practices. For example, nitrogen fertilizer being mobile in soil could be broadcast on soil surface or applied in bands with a almost similar result. So this is good. You can go for top dressing of nitrogenous fertilizer. The P fertilizer should be placed in bands in the root zone as phosphorus is comparatively less mobile in the soil. So therefore, it should be basally applied. Now next, number 2 factor that will affect the supply of the nutrients to the soil solution is cation and anion exchange capacity of the soil. In general, higher the values, higher will be supply. The clays and humus work as soil colloids. You know, there are 2 kinds of soil colloids. Organic colloids, it is mainly humus, and non-organic or mineral colloids are your clays. So they work as exchange sites because on these colloids, the nutrients are attached. Overall, the charge is negative, but that does not mean that they always have negative charge. They also have certain sites which have positive charge. From on those positive charges, the negative charge ions, that is anions, can also be attached. So on soil colloids, you will find cation and anion both are attached, but these cations always outnumber anions. So one point here I want to ask from you, what is double diffused layer? Double diffused layer. Anybody knows? DOUBLE, double diffused, DIFFUSED. Diffusion से है, diffused, double diffused layer, LAYER, layer. What is that? Double diffused layer. If you don't know, you write it on a paper and you try to Google and find it out, and then tell me what is it. I forgot what is double diffused layer. This is very important layer in the exchange of ions from colloids. So you should see it, double diffused layer. Anyway, we continue. So clays and humus are the colloids which act as a exchange sites, and cation and anions exchange occurs in soil between soil solution and exchange sites. Ion exchange is a reversible process, you know, reversible process because they are in equilibrium. So if there are excess potassium in the solution and you get less on the exchangeable side, so they can reverse. They can go back to the exchangeable side. Cation exchange is more important as the cation exchange capacity is larger than the anion exchange capacity in the most soils. So similarly, you can define anion exchange capacity as the capacity of the soil to hold, or capacity of 1 kilogram soil to hold anions. What would be the mass of cation, that anions that can be held by 1 kg soil in centimoles? This process enhances availability and retention of plant nutrients. So this is important. Cation exchange is very, very important because with the help of cation exchange capacity, soil can hold ions and increase the availability of the ions or nutrients. Soils dominated by oxides of aluminum have positive sites in acidic soils. So you know what are the minerals that make up our soil. So you need to study minerals of soil, and in those minerals you will also find oxides of aluminum have positive sites in acidic soils. So as usual, they have both charge, negative charge and positive charge, and anions can be absorbed and dissolved from them. So these oxides of aluminum can act as a colloid. Nitrate and chloride are weakly held at positive sites of the soil colloids. They are attached, but they are weakly attached and more likely to be found in soil solution because they are easily movable. They move very fast in the soil. They are mobile in the soil. Phosphate and sulfate are strongly bound to exchange site. Compared to nitrate and chloride, phosphate S2PO4 and sulfate are strongly bound to exchange sites. Anion exchange capacity increases as soil pH decreases. With the decreasing in soil pH, anion exchange capacity increases. Anion exchange capacity is much higher in acid soils. So as a student, you need to find out the reason why this anion exchange capacity increases as soil pH decreases. This is your homework. You can find it out and then tell me, discuss with me why it is so. And anion exchange capacity is much higher in acid soil. Why it is higher in acid soil? So these two questions are for you. You please find answer and tell to me. And third one is double diffuse layer. So I will not answer this question. You have to find yourself. Now, cation and anion on soil exchange surface. So we are continuing with the second factor, that is CEC and AEC. We are continuing with the same factor, but in between, let us have some knowledge of the cation and anion exchange. So except aluminum and sodium, most of the exchangeable cations are plant nutrients. So they are also in the soil, but they are not plant nutrients. But their exchange also happen. Their uptake also happen. Uptake by plant is also there. Of course, they are non-essential. In acidic soils, the principal cations are aluminum, hydrogen, calcium, magnesium, and potassium. This calcium and magnesium is there, but in very small quantities. As you increase the acidity or as acidity increases, the concentration of sodium and magnesium and this calcium decreases. So whereas in neutral and basic soils, of course, you will find calcium, magnesium, potassium, and sodium. So by chance, I don't know this Havlin written calcium and magnesium in acidic conditions. I think there is deficiency of calcium and magnesium in acid soils. Cations are adsorbed to the CEC with different adsorption strength. The strength of adsorption is different. And this strength of absorption varies with the valency. In general, higher the valency means here charge. Higher the charge, strong is the attraction. Strong is the attraction to the exchangeable sites. For example, aluminum. So you can see here, higher the charge, higher is the attraction, higher is the bondage with the clays or with the organic colloids. So for example, if it is ferric Fe3 and ferrous, so ferric will be bound more strongly than ferrous. Similarly, if it is aluminum, so aluminum strength of adsorption will be much higher than than iron or potassium or hydrogen. But interestingly, many times what I see that hydrogen is more strongly adsorbed than calcium, than magnesium, than potassium. Although its charge is just 1 + 1, and calcium has 2 charge, magnesium has 2 charge. But this hydrogen is attached more strongly than those cations having 2 charge. What is the reason? Can anyone tell me? Do you get the question? What question I asked? The question is very simple, that your calcium, magnesium has 2 charges, divalent, and cations. Hydrogen has 1 charge, but hydrogen is more strongly attached to colloids than your calcium or magnesium or potassium. Anybody? No problem. You will see it.
Sir, because the size of the H plus ion is very small, so the charge density is more than the other ions because they have larger size, that magnesium and calcium.
Correct. So why were you silent then? No confidence. No confidence in yourself. You should have confidence. No problem. This is correct answer. So now you see, for most minerals, the strength of cation adsorption is generally represented by aluminum is the strongest, strongly attached, followed by hydrogen, although it has 1 charge, but it is ahead of calcium, magnesium, potassium. So you can see calcium, then magnesium. This is strength of their attachment to the exchangeable sites. And then potassium is almost equal to ammonium, and then sodium. So it is their strength. And when the detachment comes, so sodium will be the first to be detached from the this exchange complex. Similarly, in this order, they will attach, then ammonium, potassium, magnesium. So there they will be exchanged like this. The properties of cations determine the strength of adsorption or ease of desorption. Ease of desorption. So from right side, you will get ease of desorption. From left side, you will get a strength of adsorption. Highest strength on the left side, and least on the right side. Regarding desorption, highest on the right side, least on the left side. So the hydrogen ion is unique because of its very small size and high charge density. Thus, its adsorption strength is between aluminum and calcium. So you got the answer. Adsorption strength for cations with similar charge is determined by actually size or radii of the hydrated cation. Sometimes your ions can be hydrated, they can have water. So adsorption strength for cations with a similar charge. Suppose calcium and magnesium, they have similar charge. Sodium, potassium, they have similar charge. Is determined by size or radii of the hydrated cation. As size of the hydrated cation increases, the distance between the cation and the clay surface increases. So more hydration means that can be easily removed from the clay complex or colloidal complex. Larger hydrated cations cannot get as close to the exchange surface as smaller cations, resulting in decreased strength of adsorption. We continue with the same cation exchange capacity. CEC is one of the most important soil chemical properties influencing nutrient availability. So CEC and AAC have role in the nutrient availability and retention. Soil cation exchange capacity represents the total quantity of negative charge, surface charge on minerals and organic matter available to attract cations in the solution. So that is your cation exchange capacity. Overall, it is in negative. CEC is expressed as milliequivalents per 100 gram soil or centimoles per kg soil, and on the basis of oven dried soil. The milliequivalent unit is used instead of mass because cation exchange capacity represent both the milliequivalent per 100 gram of soil, per 100 gram of negative charge, and the total milliequivalent per 100 gram of cations adsorbed to the CEC. Anion exchange capacity. Anions in soil solution are adsorbed to the positive charge sites on clay minerals edges and organic matter. So as your cations are attached, similarly anions are also attached, but attached to the positive sites on the colloidal complex. Anion exchange may also occur with hydroxyl groups on the hydroxyl surface of kaolinite. Displacement of hydroxyl from hydrous aluminum and iron oxide is also an important mechanism for anion exchange. Anion exchange, they can act as colloids from hydrous iron and aluminum oxides. Particularly in highly weathered soils of the tropics and subtropics. Anion exchange capacity increases as soil pH decreases. Further, anion exchange capacity is much greater in acid soils high in 1:1 clays and those containing iron and aluminum oxides than in soils with predominantly 2:1 type of clays. Again, this is a problem to you. You need to find out answer yourself from the Havlin book, it is there. Or you can also use nature and properties of soil to find out the reasons for this. Montmorillonite minerals usually have an AC of less than 5 milliequivalent per 100 gram, whereas kaolinites can have an AC as high as 40 milliequivalent per 100 gram. And regarding cation exchange capacity, I think it is reverse. Montmorillonite have higher cation exchange capacity than kaolinite, but kaolinite have more anion exchange capacity than Montmorillonite. Is it correct? This is anion exchange capacity. Kaolinites have more than the Montmorillonite. What is the case of CEC? Is it reverse or is it same?
Sir, in case of CEC, montmorillonite will be having more cation exchange capacity.
Yes, yes, true. So it is reverse. Now you see anions such as chloride and nitrate may be adsorbed, although not to the extent of H2PO4 and sulfate. Means they are actually strongly attached than your chloride and nitrate. The order of desorption strength is H2PO4, SO4, NO4, NO3 is chloride. So chloride can be easily removed, followed by nitrate, sulfate, and it is difficult to remove H2PO4. So this is comparative desorption. It continues. Factors influencing continues this number 2 factor, CC and AAC of the soil. So you can see this figure. These are plant roots, uptake of anions and cations. So they take up from the soil solution these nutrients, and then the soil solution will be having deficiency of the nutrients because nutrients, anions and cations are available here, but part of that has been removed by the plant roots. So it can get nutrients from soil colloids. Clay and humus are the soil colloids, and adsorb cations and anions. They can be transferred to the soil solution. So this is how, and you can see that things are in equilibrium. Things are almost in equilibrium. So exchange of cations and anions between soil colloids and soil solution, arrow 2 here. So there is exchange of ions from colloids to the soil solution. And plant roots, arrow number 1, cations of soil solution exchange for hydrogen and anions for hydroxyl. So here the hydrogen will come to the soil solution, and then the positively charged ion will go to the plant roots during the uptake. And then if the roots release hydroxyl ion, they can be exchanged with the anions. So exchange of hydrogen and anions for hydroxyl produced by roots. Exchange of cations and anions continue till an equilibrium is established. So this is how the CC and AAC are very, very important. If there is no CC and AAC, then soil will not be able to hold the ions and they can leach down easily. Now, base saturation in soil. So capacity, base saturation capacity of the soil, if it is higher, then the supply of the nutrients is higher and otherwise less. So now you see in detail how this base saturation in soil is important. It is the percentage of the total cation exchange capacity occupied by calcium, magnesium, potassium, and sodium. I think you know base saturation percentage. Sometimes numericals come on this base saturation. The base saturation is higher in soils of arid region than of humid region, number 1. Because in humid region, these bases have been washed down. This calcium, magnesium, and soils are mostly acidic. The increased base saturation in soils increases the availability of cations like calcium, magnesium, and potassium. In general, higher the base saturation, higher is the availability of cations in soil. Now, this buffering capacity, next is your buffering capacity. So one bar's base saturation capacity, other is your buffering capacity of nutrients, not pH. The ability of soil to resupply iron to the soil solution from different sources, maybe clays, maybe humus, is your buffering capacity of the nutrients or nutrient buffering capacity. It can be defined as the ratio of the concentration of the adsorbed ion and solution ion. What percentage of ions are there as adsorbed, or what is the quantity of adsorbed ion, delta Q, and solution ion, delta I. Please do remember this relationship. Sometimes such question come to your quiz exam. So the ratio of the concentration of the adsorbed ion and solution ion, because sometimes we fix question papers also in different examinations, and in particularly in ICR, it is mostly taken by ICR scientists. So therefore, sometimes you may get such kind of questions also, and many others who are not part of IRI may not know it. So that also happens. So this is important, this concentration of the adsorbed ion and solution ion. So you can say buffering capacity can be defined as the ratio of the concentration of the adsorbed ion and solution ion. Delta Q divided by delta I. Soils may vary in buffering capacity. Some have high and some have low. Low buffering capacity means some soil have very good capacity to compensate the ions, to give the ions from the exchangeable complex to the soil solution. But some have poor this buffering capacity. So generally, buffering capacity in soil increases with increasing CEC. Generally, higher the CEC, higher is the buffering capacity, higher is the organic matter, higher is the buffering capacity and other solid constituents in the soil. So this is one. Number two, the buffering capacity of Mount Morillonite, high organic matter soils is greater than that of kaolinite, low organic matter soils. So in general, because of more colloids, more organic and inorganic colloids, the cation exchange capacity is high. Therefore, higher cation exchange capacity means higher buffering capacity, means higher nutrients level can be supplied to the soil solution in case if it is removed by the plant. Since cation exchange capacity increases with increasing clay, this is another point, increases clay content, fine texture soils will have higher buffering capacity than the coarse textured soils because their cation exchange capacity is low in coarse textured soils. So therefore, their buffering capacity will be low. If exchangeable potassium decreases on exchangeable sites by plant uptake or leaching, the capacity of the soil to buffer solution potassium is lower in sandy soil. So if exchangeable K ion decreases by plant uptake, means it was there in the solution, it has been removed by the plant and there is deficiency of potassium in the soil solution. So now the capacity of the soil to buffer solution K is lower in sandy soil and higher in clayey soil. The nutrient may become deficient and K fertilizer will be needed to increase exchangeable K and correct the deficiency in sandy soil. Addition of P fertilizer will increase adsorbed phosphate, while some H2PO4 may also precipitate as solid P compounds, both of which contribute to the phosphorus buffering capacity in the soil. Thus, it is evident that buffering capacity is very important soil property that is strongly influences nutrient availability. So in general, higher buffering capacity of the soil, higher is the nutrient availability. If same rate of fertilizer P is added to two kind of soil, to both soils, same rate of fertilizer P is added to both soils, the resulting solution H2PO4 concentration or resulting phosphorus concentration in the soil solution will be greater in sandy than in clay soil. Will be greater in sandy than in clay soil because buffering capacity of clay is more than the buffering capacity of the sand, because it cannot hold this sand cannot hold more of this phosphate as exchangeable phosphate because its cation exchange capacity, anion exchange capacity is low compared to clay soil. So therefore, most of the phosphorus will be in the solution. Most of the phosphorus will be in the solution. You can read the two lines written below. Sandy soil has low CEC, low cation exchange capacity, low phosphorus fixation, and absorb less phosphate on CEC, thus more phosphate in solution than clay soil at the same rate of phosphorus application. So this is the reason that in sandy soil, if you apply the same rate of phosphorus, you will get more concentration of phosphorus in the soil solution in sandy soil than in clay soil. So if same rate of fertilizer P is added to both soils, the resulting solution H2PO4 concentration will be greater in sandy than in clay soil because of higher buffering capacity of the clay than in sand. Alternatively, if we wanted to establish the same solution P concentration. See, this is also important from management point of view. Alternatively, if we wanted to establish the same solution P concentration in both soil, then more fertilizer P would be needed in the clay soil compared to the sandy soil, again because buffering capacity of clay is more than the buffering capacity of sand. So in both the soils, if you want to get the same level of phosphorus or H2PO4 in the soil solution, then you need to apply more phosphorus in clay soil than in sandy soil. So actually, these are very general points. Several other factors will also affect your pH, your texture, structure, so many things. So these are very general kind of points to get some knowledge, some idea about this subject. Now, next is your soil pH. So you have seen many factors like buffering capacity of the soil, your cation exchange capacity, anion exchange capacity, mobility of the nutrients, and your base saturation. So number of factors you can see, they are affecting the availability of the nutrients. I can just show you again what are the factors: mobility of nutrients, CC, base saturation, buffering capacity, soil pH, soil organic matter and its decomposition, and physical condition of the soil. So these are the 7 important factors. So we have discussed up to 4, number 4, buffering capacity of the soil. Now we are going to discuss the 5th factor that affects the supply of minerals to the soil solution. Now soil pH, I think most of you are aware of that chart, soil pH and nutrient availability, that under acidic conditions, what nutrients are more available under alkaline condition. So every one of you have seen that chart. So I will not waste much time on this. Nutrients become less available to crops when soils are either too acidic or too alkaline. So you need neutral pH almost. If soils are too acidic, availability of calcium, magnesium, potassium decline, but availability of aluminum may be in excess. If pH is below 5.5 or 5, then aluminum, iron, manganese, they can become very toxic. If soils are too alkaline, then iron, manganese, zinc, copper may become less available. The availability of phosphorus is less at too low or too high pH. For phosphorus, I think highest availability is from 6 to 7. 6 to 7, you will have highest availability of phosphorus. Now, next factor, 6th factor that will affect the supply of nutrients is your soil organic matter and its decomposition. The decomposition rate or speed of decomposition or quantity of organic matter that will be decomposed. So these conditions will affect the nutrient supply. Availability of nutrients from soil organic matter depends on microbial activity in soil. So factors that affect the microbial activity will affect the soil organic matter decomposition. The important microbial processes are organic matter decomposition and denitrification. These are 2 important microbial processes. And fresh plant or other organic residues are subject to fairly rapid decomposition by microbes. Humus component of soil organic matter resists microbes. So ultimately, your organic matter is converted to humus, which is permanently stored in the soil for a long term. And before that, when mineralization happens, decomposition happens, a lot of nutrients are released from the organic matter. So those nutrients can be easily taken up by the soil solution. They will go to the soil solution. So higher the decomposition, more organic matter addition, in general will give you more nutrients release. In virgin, that is uncultivated soil, the organic matter content is determined by soil texture, topography, and climatic conditions. This topic I wish to cover in detail. Organic matter content is higher in cooler than in warmer climates, you know it, because of high temperature, faster decomposition, and with similar annual temperature and vegetation increases with effective precipitation. If you keep temperature and vegetation constant, then increase in precipitation or rainfall will increase the organic matter in the soils. These differences are related to reduced potential for organic matter oxidation in cooler temperature and increased biomass production with the increased rainfall. So there are a lot of interaction between climatic factors and soil organic matter content in soil. So that part I wish to discuss separately. Now, soil organic matter content is greater in fine texture soil than in coarse texture soil and is related to increased biomass production in fine texture soil because of improved soil water and nutrient storage and reduced organic matter oxidation potential. So yesterday we had one question that where you will get higher speed of oxidation of organic matter. Whenever we compare, we can compare under uh, identical conditions. The conditions have to be similar. If you under one kind of climate, if you have two kind of soil, one is say sandy loam or sandy soil, other is clay soil or clay loam soil. So you have two kind of soil, light texture or coarse textures and heavy textured or fine textured soil, clay soils. So they have to be in the identical climate. They should receive the same rainfall and temperature should be the same. Under those conditions, I think the organic matter decomposition will be rapid, faster in sandy soil than in fine texture soils or clay soil. For the simple reason that there will be better aeration in sandy soils. And secondly, the CN ratio, because these sandy soils will have less carbon, and the CN ratio will be narrow. CN ratio will be narrow, so I think there should be faster decomposition. And in fine texture soils, where you have more organic matter compared to sandy soil, the CN ratio will be wider. So therefore, they may have lesser speed of decomposition of organic matter. But if you find any other answer, you can share with me. Or now also, you can share your views on this topic. Anyway, soil organic matter content is greater in fine texture soil than in coarse texture soils, means sandy soils, sandy loam soils, and is related to increased biomass production. Fine texture soils, in general, this is very general statement, produce more biomass than the sandy soil under identical or under similar conditions. Increased biomass production in fine texture soils. Why? Because of improved soil water and nutrient storage. So in clay soils, you will have more organic matter and more water holding capacity, therefore more production of biomass than in sandy soils and reduce organic matter oxidation potential. So in clay soils, another reason why you have higher organic matter because of reduced organic matter oxidation potential in clay soil or fine textured soils. Soil organic matter contents are higher under grassland vegetation than under forest cover. So compared to forest cover, you get higher accumulation of organic matter under grasslands. These relations are generally true for well-drained soil conditions. So actually in Asia, we do not have much grasslands, but in certain European, American countries, your Australia, New Zealand, their larger part of their land is covered by grasslands. Grasslands, because lands are very, very undulated and there is no shortage of water, and soils are not well developed. They may be rocky kind of things. So therefore, only option for those soils is grassland. So they have very large areas under grassland and they keep animals, particularly cows. Holstein, Friesian, and such kind of cows are kept on the grassland because they cannot use those land for other purposes. So in grasslands, you get more organic matter than forest lands. These relations are generally true for well-drained soil conditions. Under poor drainage, aerobic decomposition is impeded and organic residues build up high levels of organic matter regardless of temperature or soil structure. So your drainage is poor, waterlogged condition. Under those conditions, you will get higher accumulation of organic matter compared to aerobic conditions. Soil organic matter comprises organic material at all stages of decomposition. Crop residues degrade through autotrophic and heterotrophic microbial processes that ultimately form relatively stable organic matter, that is humus. The size of these components depends on climate, soil type, and soil and crop management, all of which influence the quantity of crop residues produced and returned to the soil. So these details I will teach you separately, but here purpose is that when you have organic matter in the soil, it is decomposed, it is oxidized, or it is reduced, whatever way it is reduced, ultimately it also releases nutrients. So the contribution of organic matter, if it is higher, then the supplying capacity of the nutrients will be higher. It is very simple to explain. Fresh plant or other organic residues, whenever they are added into the soil, they are attacked by heterotrophic organisms and they release the nutrients and nutrient availability is increased. So then also humus is very, very important, soil humus, because upon decomposition of organic matter, you also get humus levels increased. And you know the role of humus in plant growth. Humus can directly stimulate the plant growth. It acts as a growth promoting substance, humus, and it increases water holding capacity, nutrient availability, and many other properties important to soil productivity. So in general, higher the humus, higher is the, even sometimes humus will also get decomposed, but of course it takes a lot of time, 100 years or more. But in the end, because it contains nutrients like nitrogen, so it will release nutrients into the soil upon its own decomposition. Now you can see the primary soil microbial processes involved in fresh residue and organic matter turnover or cycling are mineralization and immobilization. So you can see these are happening mineralized. So they supply, these mineralization supplies nutrient to the soil solution. Now, if the decomposition process, soil organic matter gives nutrients in inorganic form. So decomposition process will give you nutrients. And if there are insufficient nutrients in soil organic matter to meet the microbial demand, then the inorganic ions from soil solution will be immobilized into the microbial cell. So here you can have temporary nitrogen deficiency in the soil and for the crop. The microbial activities and rate of release of nutrients from soil organic matter is affected by CN ratio of the soil organic matter. So normally, narrower the soil CN ratio less than 24 or so, then you will get mineralization. And if it is 24 or 30 or more than 30, then you will get immobilization. So it depends upon CN ratio of the organic material. In different books, in different papers, these kind of information are different. In some cases, I have seen they say less than 30 CN ratio means you will get mineralization. More than 30 CN ratio, you will get immobilization. In some cases, I have seen 24, less than 24, more than 24. So they are quite variable figures and values of CN ratio. So a lot of confusion is there. So we don't have one answer to this. It will depend upon temperature, water availability, many climatic factors, soil factors that encourage the relationship of, or that involves the relationship of mineralization and immobilization. So we cannot have one fixed figure of CN ratio. I really scanned a lot of literature to find this CN ratio, but values are different. So then last thing is physical condition of the soil. Physical condition of the soil will also affect the nutrient supply to the soil solution. Poorly structured soil increases the soil erosion by runoff, losing valuable nutrients. Means even your soil solution will go away. It will move away from the soil along the soil erosion, losing valuable nutrients, soil microbes, and organic matter. So erosion can disturb the availability of nutrients, and it decreases the cation exchange capacity also because minerals and organic matter is also removed from the topsoil. Poor soil structure can restrict the root growth and thus reduces the access to the available nutrients. Because sometimes if you get more root growth, it can explore larger volume of soil. So it may come in larger contact of nutrients. If root growth is restricted, it will get in the contact of less volume of soil. Therefore, nutrient availability to the roots will be less. Optimal level of soil water is also necessary. You don't want too much and too little. You want right quantity of water in the soil. Then adequate moisture also increases the rate of soil organic matter decomposition. Poorly drained soils increase the solubility of minerals like iron, manganese, because poorly drained soils increase the solubility of minerals like iron, manganese, making them sometimes toxic to the plants. It depends upon soil pH. Nitrates can be lost due to denitrification in flooded soils. Low moisture can result in reduced nutrient. So water means physical condition will affect the availability of the water. Availability of the water, growth of the roots, and movement of ions, accessibility of ions or nutrients. So many direct and indirect effects will be there on the nutrient availability as far as physical condition of the soil is concerned. Poor the physical condition of the soil, poor is the supply of nutrients to the soil solution. Poor soil condition means it can be waterlogged, it can be drought, it can be your hard pan, it can be soil compaction, or it can be reduced root growth due to poor physical condition of the soil. So all these are going to affect the nutrient availability. That completes this lecture on this factor affecting the supply of nutrients. Problem of supply and availability of nutrients. We got 4 minutes time is still left. So if you have any question, you can ask.